Welcome to the final chapter of our Chiral Phonons series. In this chapter, we bridge theory and application by covering computational methods for calculating phonon chirality and exploring emerging applications in valletronics and phononic devices. You'll learn how to extract phonon angular momentum from DFT calculations and discover device concepts that leverage chiral phonons for information processing. By the end of this chapter, you'll be able to calculate phonon eigenvectors and extract circular polarization from DFT results, compute phonon angular momentum using the standard formula, set up phonon calculations with phonopy and quantum espresso, understand PAM transport phenomena, including the phononic Einstein-de Haas effect, apply chiral phonons to valletronics, and explore emerging device concepts like phonon transistors and polarizers. The calculation of chiral phonons from first principles follows a systematic workflow. First, we optimize the crystal structure using DFT relaxation. Next, we calculate force constants using either phonopy's finite displacement method or density functional perturbation theory. We then diagonalize the dynamical matrix to obtain eigenvalues and eigenvectors. From the complex eigenvectors, we extract circular polarization and finally compute the phonon angular momentum. The dynamical matrix D captures the force constants in reciprocal space. The matrix elements depend on atom indices kappa and kappa prime, Cartesian components alpha and beta, atomic masses m, and the phonon wavevector Q diagonalization yields phonon frequencies omega j squared and eigenvectors, e.g. the eigenvectors are complex vectors that encode both amplitude and phase of atomic displacements. The circular polarization vector C is obtained from the imaginary part of the cross product of the eigenvector with its complex conjugate. For in plane motion in 2D materials, the Z component simplifies to CZ equals the imaginary part of EX star times EY minus EY star times EX positive CZ indicates counterclockwise motion, which is left-handed chirality. Negative CZ means clockwise motion, right-handed chirality. The total phonon angular momentum per unit cell is obtained by summing over all atoms with mass weighting. The formula is Lj equals h bar times the sum over kappa of m kappa times Cj kappa. The result has units of h bar per phonon, representing quantized angular momentum. This is the key quantity that determines chiral character and couples to electronic degrees of freedom. Phonopy is a Python-based phonon calculation tool that interfaces with various DFT codes including VASP, Quantum Espresso, and Abinet. Key capabilities include the finite displacement method for force constants, phonon dispersion and density of states calculations, extraction of eigenvectors at arbitrary Q points, and group theory analysis of phonon modes. Installation is simple. Just pip install Phonopy. Quantum Espresso is an open-source DFT suite with powerful phonon capabilities through density functional perturbation theory. The PWX module performs ground state DFT calculations. The PHX module calculates phonons using DFPT, which is particularly accurate for polar materials with long-range electrostatic interactions. The DINMAT X module handles post-processing of dynamical matrices. We implement a Python PAM calculator class that takes a Phonopy object as input. The calculate circular polarization method computes CZ equals 2 times the imaginary part of EX conjugate times EY for each atom. The calculate PAM method performs the mass-weighted sum to obtain total and per atom angular momentum. These functions form the computational core for analyzing phonon chirality. The PAM calculation algorithm proceeds in clear steps. First, set the Q point of interest. Second, extract the complex eigenvectors from Phonopy. Third, for each atom, calculate CZ from the eigenvector components. Fourth, sum with mass weighting to get total PAM. Fifth, visualize by plotting frequency versus PAM to identify which modes are chiral. Modes with large absolute PAM are the chiral phonons. Let's apply this to monolayer WSE at the K point, which is at fractional coordinates 1/3, 1/3, 0. Running the PAM calculator identifies chiral modes by filtering for absolute PAM greater than 0.1 and frequency above 0.5 terahertz to exclude acoustic modes. The output lists mode index, frequency in terahertz, PAM in units of h-bar, and whether the mode is left or right-handed. For quantum espresso, the workflow starts with a self-consistent field calculation using PWX. Then PHX calculates phonons at the K point using DFPT. The input file specifies the prefix, output directory, dynamical matrix file name, and the Q point coordinates. Finally, DINMAT, X post-processes the results. Eigenvectors can then be extracted and processed with Python to calculate PAM. Now let's explore phonon angular momentum transport phenomena, including the Einstein-de Haas effect for phonons, phonon spin currents, and thermal Hall effects arising from chiral phonons. The Einstein-de Haas effect demonstrates angular momentum transfer between different degrees of freedom. For phonons, excitation of chiral modes carrying angular momentum L phonon could induce mechanical rotation of the crystal lattice to conserve total angular momentum. This was theoretically proposed by Zhang and Niu in their 2014 Physical Review Letters paper. Experimental demonstrations of a phononic Einstein-de Haas effect remain an active area of research, with ongoing efforts to detect the predicted lattice rotations. The magnitude of the effect depends on the specific material and experimental geometry. Analogous to electronic spin currents, phonon spin currents represent flow of angular momentum without net energy transport. The phonon spin current density is the sum over modes of PAM times group velocity times occupation number. This provides a mechanism for angular momentum transport in insulating materials where electronic spin currents are not available. Phonon spin currents can be generated through several mechanisms. Thermal gradients drive phonon flow with net angular momentum if there's asymmetry between chiralities. Optical excitation with circularly polarized light selectively excites one chirality. Ultra-fast laser pulses can generate coherent chiral phonon populations through impulsive stimulated Raman scattering. The thermal Hall effect is transverse heat flow perpendicular to a temperature gradient. In materials with broken time reversal symmetry, chiral phonons contribute to the thermal Hall conductivity through their Berry curvature. The formula involves an integral over the Brillouin zone of phonon heat capacity, group velocity, and Berry curvature. This connects phonon chirality to measurable transport coefficients. The phonon-Nernst effect is a theoretically proposed phenomenon where a transverse voltage could be generated from a thermal gradient through a chain of processes. In this model, a temperature gradient drives chiral phonon flow carrying net angular momentum. Valley-phonon coupling would transfer this angular momentum to valley carriers. The resulting valley polarization could induce a transverse electric field through the Valley-Hall effect. While this provides an intriguing concept for electrical readout of phonon angular momentum transport, experimental verification remains an active research goal. Let's now explore applications of chiral phonons in valletronics, including valley manipulation, intervalley scattering control, and valley information storage. Valley-phonon coupling in 2D TMDs follows specific selection rules based on angular momentum conservation. At the K-valley, excitons have angular momentum +1 and couple to left-handed phonons via sigma plus optical excitation. At K', excitons have angular momentum -1 and couple to right-handed phonons via sigma minus light. These selection rules enable valley-selective manipulation through chiral phonons. Valley initialization can be achieved through phonon-assisted processes. Sigma plus optical pumping creates K-valley excitons. During relaxation, these excitons emit chiral phonons carrying PAM equals plus h-bar. Momentum conservation ensures the total angular momentum is preserved. This provides a mechanism for initializing valley states with specific chirality. Intervalley scattering from K to K' can occur through absorption or emission of chiral phonons. The scattering rate is proportional to the electron-phonon coupling squared times the phonon occupation factor. At low temperatures, phonon occupation is suppressed exponentially, leading to longer valley lifetimes. This temperature dependence is key for applications requiring long valley coherence. Chiral phonons enable valley information storage by encoding binary information in the valley index. Bit 0 corresponds to the K valley with angular momentum +1. Bit 1 corresponds to K' with -1. Writing uses sigma plus laser pulses for 0 and sigma minus for 1. Reading detects valley-selective photoluminescence or valley Hall voltage. The coherence time at room temperature ranges from picoseconds to nanoseconds. We can simulate valley phonon scattering dynamics with Python. The valley phonon scattering class takes temperature, phonon frequency, and coupling strength as inputs. It calculates phonon occupation using Bose-Einstein statistics, intervalley scattering rate, and valley lifetime. Plotting lifetime versus temperature shows the exponential increase at low temperatures, consistent with thermal suppression of phonon-mediated scattering. Now let's explore emerging device concepts that leverage chiral phonons for information processing and signal manipulation. Chiral phonons offer several advantages for information processing. They operate at low power compared to electronics. Terahertz frequencies enable ultra-fast switching. Phonon coherence times can reach nanoseconds, and direct coupling to valley degrees of freedom enables integration with valletronic logic. Proposed logic gates include AND gates where opposite chiralities annihilate, NOT gates for chirality reversal, and XOR gates detecting chirality mismatch. A chiral phonon transistor modulates phonon angular momentum current using an external control. The source generates chiral phonons, for example via sigma plus laser on a TMD. The channel is a 2D material where valley phonon coupling can be controlled. The gate applies electric field or optical pulse to modulate valley polarization. The drain detects phonon angular momentum, perhaps via thermal Hall effect. Gate voltage changes scattering rate for chiral phonons. Phonon polarizers selectively transmit phonons of specific chirality. 3 design strategies exist. Symmetry-based filtering uses broken mirror symmetry, where one chirality couples strongly to electronic states and is absorbed. Resonant filtering designs a cavity with chiral resonance at specific frequency. Valley selective filtering applies valley polarized carriers via optical pumping, where matching chirality phonons are absorbed. Performance metrics include extinction ratio and bandwidth. A phonon circulator routes phonons unidirectionally based on chirality, enabling non-reciprocal transport. A 3-port design sends left-handed phonons from port 1 to port 2, right-handed from port 2 to port 3, and neutral phonons from port 3 to port 1. This provides phononic signal routing for integrated phononic circuits without backskittering. Let's examine chiral phonon polaritons, hybrid quasiparticles arising from strong light-matter coupling, where the phonon chirality is transferred to the photonic component. Phonon polaritons form when photons and phonons hybridize through strong coupling. The coupling Hamiltonian includes phonon and photon terms plus an interaction term with coupling strength G when the phonon carries angular momentum. The resulting polariton inherits chirality. This creates a hybrid excitation with both photonic and phononic character, combining the advantages of both. In the strong coupling regime, where G exceeds the damping rates, the dispersion splits into upper and lower polariton branches. The energies are given by E plus and E minus, separated by the Rabi-splitting omega r equals 2G. The anti-crossing and the dispersion relation is the signature of strong coupling. This splitting is observable in spectroscopy experiments. Chiral phonon polaritons have several applications. They can serve as tunable THZ sources emitting circularly polarized radiation with controllable helicity. In quantum optics, single phonon polariton sources could provide quantum bits for information processing. For nonlinear optics, the combined chirality of phonon and photon enhances second harmonic generation and enables chirality transfer between optical frequencies. Looking to the future, several research directions are promising. Quantum phononics aims to use chiral phonons as qubits with chirality encoding quantum information and creating entangled phonon pairs. Topological protection could yield robust phononic states through edge states and Weyl phonons. Room temperature operation requires materials with large energy splitting and ultrafast dynamics. Technology integration means combining phononic elements with CMOS and optical interconnects. Several challenges remain for quantum phononics with chiral phonons. Decoherence from phonon-phonon scattering limits coherence times. Single phonon sources are difficult to generate and detect reliably. Thermal occupation of phonons at finite temperature limits quantum fidelity. Promising materials include hexagonal boron, nitride with its large bandgap, and stable phonons, and engineered heterostructures with tailored valley and phonon properties. Let's summarize Chapter 4. We covered DFT calculations for extracting circular polarization C equals the imaginary part of E star cross E, and PAM equals H bar times mass times C. We explored PAM transport phenomena including the Einstein-de Haas effect and thermal Hall effect. For Valletronics, we saw how selection rules enable valley manipulation and information storage. Device concepts include transistors, polarizers, and circulators. And phonon polaritons provide strong light matter coupling with chiral character. This concludes our 4-chapter series on chiral phonons. In Chapter 1, we established theoretical foundations including phonon angular momentum, symmetry requirements, and Berry phase. Chapter 2 explored chiral phonons and materials from 2D TMDs to 3D chiral crystals. Chapter 3 covered experimental detection techniques and key results in WSE2 and alpha quartz. And Chapter 4 presented computational methods and applications. Chiral phonons represent a frontier of condensed matter physics with rich opportunities for fundamental research and technological innovation. Thank you for joining this journey.